Welcome back to the channel. Today we're going to talk a little bit about trigonometry, different ways that I can calculate, say, the sine, cos, tan of various angles, at least readily and easily at my disposal, without using a calculator. An example might be, say, using a special angle. So pi over 3 is 60 degrees, and most of us know our special triangles. So say if this is pi over 3 right here, I know the opposite side is root 3. The hypotenuse is 2, this is 1. And so the sine of pi over 3 is root 3 over 2. So that is a nice way to do it. The problem is sometimes the angle isn't special. So let's say it's pi over 12. Well, we can get a little clever, I guess, here by recognizing that that's the same as, well, 4 pi over 12 minus 3 pi over 12. And I can expand that out. You see, that would be the same as the sine, cos, sine. 4 pi over 12 is pi over 3. And 3 pi over 12 is pi over 4. Repeat those here. Pi over 4. Put a minus in the middle. We know what the sine of pi over 3 is. We know what the cosine of pi over 4 is, root 2 over 2. You could plug them in and do a little bit of arithmetic, and that would be kind of nice. Another way might be to think a little bit about the actual sine wave. So I'm focusing on sine, but we could have a similar conversation about tan and cosine. The sine wave looks a little bit like this, at least near the origin, right? So if this is the sine pattern, I know the wave is going to continue to go on like that. We're just going to talk in radians here to keep it focused. Maybe what I could do is I could construct. Is there a possibility that I could build a function that at least near the origin looks similar to the sine wave? For instance, maybe I could build something that looks like this. That's a polynomial. You know, it's got some curvature to it. And maybe I could construct a polynomial that at least near some center, the center here could be the origin, although that could be adapted for any location along the x-axis, for which at least around that center, the red curve is a pretty good estimator for the sine wave. And there's actually a way to do that. So that's kind of what I wanted to talk about here. So what I'd like you to know is that the sine wave, I'll just call it f of x, equals the sine wave, can be estimated using a polynomial. This is a Taylor polynomial, and it's an algorithm, and it can construct for you a polynomial that you could use some simple mathematics on, use it as an algorithm. So I'm going to assume that we're the center, or the focus of accuracy, we want it, say, at 0. So right at that origin where x is equal to 0. So in this case here, what I could do is, at least I know I'm stationed at 0. So why not take the function at 0? So that could be like my y-intercept. And then I could also build a linear term. Now think about it here for a moment. The linear term has a coefficient on it called the slope. And why not just take the slope of the function that I'm concerned about as a metric for the slope of this approximating line? So I'm going to take the derivative of sine at 0, and then that will be my coefficient, my slope, for this linear approximator for the sine wave. I don't think that's going to do it very well. I'd like a little bit of curvature, so let's curve this out. Let's add a quadratic term. So I'm going to add a quadratic in. Again, when just using this idea of coefficients, then the coefficient for the quadratic will be the second derivative. Again, we're centering this at 0. I'd like that accuracy at 0. Times the quadratic. Just a little sort of curveball here. I do have to adjust the coefficient for a factor of 1 over 2 factorial, which may not be intuitive, but it is an important part of the polynomial that I'm building here. I could add a cubic. So let's add a cubic. So if I'm following this idea, so there's been no derivative, first derivative, second derivative. Let's take the third derivative. At 0, there's your cubic, and divide that by, well, 3 factorial. So let's take the fourth derivative. So the fourth derivative at 0 for the quartic term, which again is going to allow us to build more accuracy, in our approximating, our polynomial approximator for the sine wave. Again, the intuition there would be to carry this. Look, 2 factorial, 3 factorial, 4 factorial. The fifth derivative at 0, and that's going to be for the quintic, all over 5 factorial. And of course, that could continue on for quite some time. Well, f at 0, well, f at 0, that's sine at 0, which is just 0. And f prime, well, what's the derivative? I'll just place it down here. So my approximating function for the sine wave is going to be 0 plus the first derivative of sine. Well, the derivative of sine is cosine. So it's going to be the cosine evaluated at 0 times x. And so the second derivative, well, that's going to be the derivative of cosine. The derivative of cosine is negative sine. So negative sine, evaluate that at 0 for my degree 2 divided by 2 factorial. You can see that that's going to go to 0 as well. Okay, the third derivative is the derivative of the second derivative. So the derivative of sine is cosine. So negative cosine at 0 for my cubic. I have to make sure I correct by dividing by 3 factorial. That's going to make sure that that accuracy is there for you. And then I'm going to add the next one in. So the derivative of cosine is going to be negative sine, negative, and a negative is a positive. Positive sine at 0 over, well, 4 factorial. 4 factorial times x to the 4. One more, so I'm going to take the derivative of sine, which is cosine, at 0 divided by 5 factorial times degree 5 for your polynomial. And that's just going to continue on for a while. And then notice what sine is being approximated by. So I have an x, the x stayed. And then this dropped out. Well, this one here is negative cosine of 0. Well, that's negative 1. So I'm going to get negative x to the 3 over 3 factorial. I lose this term because the sine of 0 is 0. The cosine of 0 is 1. This is going to be a positive term, x to the 5 over 5 factorial. And you can kind of predict some more terms here. Do you see? So if I was to predict, it looks like it's alternating, positive, negative, x to the 7 over 7 factorial. The next one is going to be positive x to the 9 over 9 factorial minus, and that'll continue on. And I will tell you this, and I'd like you to try it out. If you choose angles close to 0, then even after just a couple of terms, your function, your approximating function, is going to be really close to sine. It'll diverge after a certain point, but when you're close to your center, and our center here is 0, then you get a pretty good approximation. By the time you get to the third or fourth term, you'll be really surprised. I want you to try that out on your own. So notice here, sine wave can actually be sort of summarized as an infinite series. That's an infinite series of terms. It's a polynomial. And that means if it's infinite and it's a series is summing up. So here, I'll just use the letter k, and maybe I'll start at 0 and go all the way to infinity. And here you can see that I have an alternating series, meaning negative 1 is going to want to show up and alternate. So I'm just going to choose that to be k. And you can see here that if k is 0, that means it's going to be positive. When k is 1, it's going to be negative for the second term, so that looks pretty good. I also have an exponent on the particular polynomial power, and that is my odd terms, or odd numbers, 1, 3, 5, 7, 9, and so on. So I could use 2k plus 1, which is going to generate those odd numbers. And also I have a number in the denominator that matches the exponent. So that's going to be 2k plus 1 factorial. So there's a nice succinct way of writing the sine wave, the sine function, using a polynomial, and you can cut that off at any place you want to. This is obviously going right to infinity, but you can terminate it, you can cut it off, just take the first few terms. You could plug that into your calculator or do it by hand if you wanted to, and you'll see that you're going to get some pretty good estimators. So as a takeaway here, here's some homework for you. You can use your Taylor or your Maclaurin series polynomial to get an estimator for, say, the sine of pi over 3. So you know what that's equal to, just using your special triangle, and then start typing it into the polynomial, taking it out 1 term, 2 terms, 3 terms, 4 terms, and just see how accurate that polynomial is to estimate. All right, there you go. Today, that's a little crash course in the Maclaurin series. It's a Taylor polynomial centered at 0. And just another way that we can figure out what the sine or cos or tan of angles are if we can't use our special triangle or we don't have access to a calculator. These polynomials can be really helpful. All right, if you liked the video today, don't forget to slap a like on it. Don't forget to subscribe, and I'll see you back here in the next video.